Students, I hope that you are doing well now. We started Unit 6 last time, and I'll take you to where we stopped last time. We were discussing Ampere's law. It tells you about the magnetic field strength of a current carrying wire, and we call it circulation sum. Let's discuss it a little bit. So, if you have a current carrying wire, what Ampere says is like that. It has to be a straight, infinitely long wire. As current flows in one direction, let's say, a constant current, how strong is the magnetic field at some given distance here? To find that, Ampere said, at that particular point, you determine B and dot it with a small distance element, B dot delta S, as it shows here, S or delta L, length element, you can see here. So, let's say I'm here. How strong is the magnetic field? Magnetic field strength at this point, dot a small distance or displacement element, plus, again, B dot. It could be another B, not necessarily the same B. B dot delta L plus. You keep on doing like that, and you go around the wire. And he said, the sum of B dot delta L is equal to the sum of a constant mu0 times the sum of currents in the distance or and the path along which you travel. So in that circumference area, as you can see from here. So if you have only a single wire, then and there is only a single current, you have mu0 times R. Actually, if you are wise enough and you keep the same distance from the wire, you argue that the B at this point and the B at the next point will not be different in magnitude, not in direction, in magnitude. So B times, you get delta L times cos 0 degree, because magnetic field strength, direction and displacement are in the same direction. Right hand rule of magnetic field strength, do you remember? The magnetic right hand rule of a single current carrier wire. So you get cos 0 degree. Cos 0 degree is 1. So you have the sum of it. Since B is constant, B will be factored out. I said B is constant if you are at the same distance from the wire in all directions, meaning you are moving along a circle. So you have B times the sum of delta L. So if you travel along a circle, the sum of delta L will give you circumference. As you know, circumference is beta 2 pi r. So you get B times 2 pi r is equal to mu0 times r. There you are. If you can measure the current, and this is constant to permeability, constant, and since the distance you can easily determine, B of a current carrying wire is not. Therefore, B equals mu0 times I divided by 2 pi r. That's all. That's what this problem discusses. Let's go back to this problem and see if you can solve it easily. Homework 21. It says, determine the magnetic field strength at a distance of 5 centimeters from a current, CC means current carrying, from a current carrying wire of current equals 2.4 amperes. So, you say, solution, and the distance is equal to 5 centimeters from the wire. The current is 2.4 amperes. Permeability is given somewhere. As you can see, it's also given here. It's a constant. So the required quantity is how much is the magnetic field strength of the current carrying wire at a distance of 5 centimeters. Perpendicular distance, by the way. At the distance of 5 centimeters from the wire. So the formula, since it's something that we determine experimentally, you have to study it by heart. You say this implies B is equal to mu 0 I over 2 pi r. Substituting, you get 4 pi times 10 to the power of minus 7. It's an SI units, Tesla meter per ampere, times the current is 2.4 ampere divided by 2 pi r, 5 centimeters. 2 pi times 5 centimeters. You have studied prefixes by heart, so you get 10 to the power of minus 2 ampere. Meter. So you can see here, meter in the numerator, meter in the denominator will cancel out. Ampere here at the top and ampere here under the dividing line. The two also cancel. There remains only T, Tesla. So 2 pi cancels 4 pi, you get 2. It's a very simple problem now. You have 2 times 2.4, this one, times 10 to the power of minus 7, divided by, remember, by 2 pi we cancel 4 pi, we got 2 here, and I have 5 times 10 to the power of minus 2. And the unit, Tesla. So how much is this? It's not a big deal. If I were you, I'll solve it. There are many ways of solving the problem, but find a mathematically simple method. 10 to the power of minus 2, cancel 10 to the power of minus 7, and get 10 to the power of minus 5. Instead of cancelling by 5, I have an easier method. Multiply by 2 here. When you multiply by 2 here, you get 10. Multiply by 2 here too. Numerator and denominator by 2. 2 over 2. So 2 times 5 gives you 10. When 10 comes to the numerator, it becomes 10 to the power of minus 1. With 10 to the power of minus 5, it gives you 10 to the power of minus 6. So we have like this. Times 10 to the power of minus 6 Tesla. How about the numbers? So 2 times 2, 4. 4 times 2.4. 4 times 4 is 16. 4, 1 would be carried over to the left. 4 times 2 is 8. 8 plus 1 gives you 9.6. So 9.6 times 10 to the power of minus 6 Tesla. Either you can call it like that, or you can use a prefix and call it 9.6 micro Tesla. That's it. Now let's go over to another topic here, in which we apply Ampere's law. By the way, since you're going around the wire, it is called Ampere's circulation sum. Then you find the name here. The summation is called circulation sum. So the next topic that we have to pick is an application of Ampere's law, and we want to know how much is the magnetic field inside. Let's come over here. Inside a thick wire like this, as you see in the drawing. And so to find the magnetic field strength, we apply Ampere's law. We say B equals mu 0 I over 2 pi r. But the problem is now, we have a thick wire. You are, let's say, somewhere inside the wire at some distance r, as you can see here. And the radius of the wire is something different. In that case, what will you use for I, and what would you do for r, and how do you get B? There is another formula which you have to apply. Experiment showed that when current flows through a thick wire like this, the current density is the same everywhere at whatever distance you are from the center of the wire. JR equals JR. This is very important, that the current density at some smaller distance than the radius of the wire and out to the end of the wire, meaning capital radius of the wire, the current density is the same. And I hope that you remember current density is current divided by the sectional area. When you apply or use the two formulae, then you can get the magnetic field strength inside the wire at any distance from the center of the wire. Here it's a bit difficult to show show you where you measure distance from, but you can see distance will be measured from the center of the wire outward. Up to here is the radius, and anywhere less than that you have a small letter r. So, how much is the magnetic field strength? This I is the whole current inside. But if you want to find out the magnetic field strength to some distance r, this must change. I is wrong. You have to write down the corresponding current. So write down IR. What does IR mean? The current within the radius of small letter r. So at any distance, how much that? We carry on with this thing here. JR means current divided by area. And inside the circle, cross-sectional area, as you know, is pi r squared. So we have I over pi r squared. And this one here too is IR. Remember, the difference between this IR and this one is, this is only a small portion of the current, this is the total current, divided by, again, the small cross-sectional area, pi r squared. So when you equate the two, you see, pi cancels pi, and therefore you get the small current IR within a smaller distance of small letter r is equal to I times pi r squared divided by pi r squared. Now you can see pi and pi cancel out, so we get the total current I times r squared divided by r squared. That gives you the current within some specified distance. So if you want to find the magnetic field, then we have to apply Ampere's law. B, therefore, equals mu 0 IR over 2 pi r. You can get I, but it's difficult to get IR. So how do you get IR? From this simple formula, the JR, your current density within any specified volume is constant. Therefore, IR we get here and substitute it in here. So I get B equals the magnetic field strength at any given distance inside the wire is equal to mu 0 over 2 pi r times IR. And IR is I times r squared over r squared, small letter r squared. Now you can see that this small letter r cancels one of the r's over here. And at any distance then, B equals mu 0 R, the current, the total current is a constant. What can change is only your distance from the center of the wire divided by 2 pi r squared. So the formula is actually simple, but you have to remember two things. That the current density is constant and Ampere's circulation is law. So let's look at homework 22. It says, find the magnetic field strength inside a current carrying conductor of radius 4 millimeters at a distance of 3.6 millimeters from the center of the conductor when it carries a current of 2 amperes. You see, this is very, very simple. An application of this formula here. So, let's write down, start by writing down the solution. You have a current carrying conductor, harm to the radius, capital letter R, is 4 millimeters. Do not convert it into meter because it may not be necessary. It might cancel out. So, at a distance of 3.6 millimeters from the center of the conductor. So that is small letter R is 3.6 millimeter, and the current is 2 amperes. This is the current in the total wire within R, not within the small radius. That you have to understand. So the question is, how much is the magnetic field strength within this distance, BR? So therefore we say BR equals, according to this formula, mu 0 R times I divided by 2 pi r squared. Now we substitute simply the values. Mu 0, as you remember, is 4 pi times 10 to the power of minus 7. Tesla, meter, or ampere. And that times 3.6 millimeter. It's not yet the time to convert it into meters later on. There will come time. So the current is 2 amperes divided by 2 pi times r squared. R is 4 millimeter times 4 millimeter. You can see, let's start with the units first of all. Since we are talking about magnetic field strength, we have to get Tesla. In the future, you have to convince yourself that when you use only SI units, the final answer will be SI units, and then you can drop all the units and write down, save yourself time, and write down only the SI unit. So, ampere cancels ampere. This millimeter cancels this millimeter. So you see, I have meter, ampere, millimeter. This millimeter has got to be converted into meter, and now you can see meter will cancel meter, and the final answer will be in Tesla. So, how do you do it? It's very simple. Let's do two things at a time. 2 pi cancels 4 pi, you get 2 times 10 to the power of minus 7 and times 3.6 times 2 divided by, remember 2 pi cancels 4 pi and we have only 2. So I have here 4 times 4 millimeter. Milli is a prefix, so to convert it into meter, all you have to do is use 10 to the power of minus 3 for milli. So, Tesla meter. Now you can see meter cancels meter. It was not necessary from the start of converting 4 millimeter into meter and square meter and so on. So, how much does this result become? I think it's a very simple thing. Remove this decimal point. Along with this one, you get 10 to the power of minus 8. With this 10 to the power of minus 3, you get 10 to the power of minus 5. So I have times 10 to the power of minus 5. Something here. What? Tesla. And by 2, 1, by 2, 2. Don't forget that. 2 cancels this 2. 2 times 2, 4 cancels 2. By 4, 1, by 4, 9 here. So you have 9 times 10 to the power of minus 5 Tesla. That's the answer. If you want to express it in prefixes, multiply by 10 to the power of minus 1 and multiply by 10. So you get 90 micro Tesla.